Everyone, welcome back to another video by Room 5. After having studied entropy, in today's video we are starting with the concept of the Gibbs free energy. This value is the final combination of the enthalpy and the entropy to give us a final estimation of what reactions are feasible and what reactions are unfeasible. A feasible reaction is the one which will, once it's started, it keeps on going. And the unfeasible reaction needs a constant supply of energy input. So how do we calculate the Gibbs free energy? Because I don't want to go into the extra unnecessary details. So Gibbs free energy, which is denoted by delta G or G in that case, is calculated by the formula minus T change in entropy total. Now the question is, what is total entropy change? So total entropy change means the entropy change of the system plus the entropy change of the surroundings. Now we know what's, let's say total, So we know what is the system entropy change, which is the entropy of products minus the entropy of reactants. But what do we mean by the entropy change of surrounding? So entropy change surrounding means how much free energy is made to release in a reaction, basically, to be dispersed into the surroundings, to be dispersed into the surroundings. Now we can just, without even mathematical calculation, we can know that if it's an exothermic reaction, it's releasing more energy, so more energy will go out and disperse into the surrounding. And if it's an endothermic reaction, it's absorbing energy, so less energy will go out and disperse into the surrounding. But how do we calculate that mathematically? So for that we have the formula that entropy change for surrounding is equals to negative enthalpy change divided by temperature. Now we have two possibilities, either for an exothermic reaction or for an endothermic reaction. If it's an exothermic reaction, enthalpy value is equals to negative, but the formula which has already a negative in it will give us the value of a positive number, which means more entropy change, like we already predicted that exothermic reactions can give more entropy change for the surrounding. For an endothermic reaction, the enthalpy change is a positive value, but the formula with its own negative makes it a negative final value. That means less entropy change, like we already predicted. Now this gives us an estimate for the surrounding entropy change, which can be put into here. So moving on with our calculation, which is this one, let's go back. Entropy change was equal to negative T change in entropy, negative T change in entropy total. Gibbs free energy is equals to negative T. Now we got systems entropy, and then we got the surroundings entropy. G is equals to negative T. For system we don't change it, so we let it stay as system. But for this value we multiply it by negative T, so it becomes negative T change in entropy of the surrounding. Gibbs free energy is equals to negative T delta S system, and then it becomes negative T. For surrounding we put in the value which was found here, negative enthalpy change over T. So negative enthalpy change over T. When we solve it, we get to know that the negatives cancel each other, the T's cancel each other. We get Gibbs free energy is equals to negative T delta S for system plus enthalpy. Rearrangement gives us del H minus T delta S. This is our final equation for Gibbs free energy calculation. Now notice that this equation has two terms. This is the first term, which is the enthalpy change of that reaction, and we have a second term, which is basically the T delta S term that determines the entropy value contributed by this reaction. The Gibbs free energy can have three possible kinds of answers. It can have a negative value, it can have a zero value, or it could have a positive value. A negative final Gibbs free energy means the reaction is feasible and it will go on even if there is no constant energy input. A positive value means it's an unfeasible reaction and it will continue to need energy input. A zero means a reaction is at equilibrium and now it can be changed into feasible or unfeasible reaction by little effort, as we will see shortly. In order to find the feasibility, we have to consider both these terms, this term and this term. So let's study two cases to make our understanding more concrete. Imagine I'm talking about an exothermic reaction in case 1 with a negative entropy change. Now you have always studied that exothermic reactions give feasibility, but negative entropy reactions are not that feasible. So what's going to happen in such a case? Let's consider it. When you put the equation, which is Gibbs free energy is equals to delta H minus T delta S. Here the entropy value is taken as negative because we already said that. So it's a negative entropy value. The T comes from the equation, the minus comes from the equation, and enthalpy change is obviously again negative. So delta G is equals to this. If delta S is equals to negative, then T delta S is also negative because temperature is always a positive value. But minus T delta S becomes a positive value because there is a minus in the equation. And due to this positivity, because of this positive value, you can expect that negative enthalpy is now in the same equation with a positive T delta S value, because I have put this positive here like this. So what will be the final answer? Is it going to be negative or positive? That depends on the value. If enthalpy change was bigger, then this negative value would be bigger and answer can be a negative value. But if the T delta S value was bigger, and because of the T delta S value, the positive part of the equation is bigger, then answer can be positive itself, the final answer. What does it depend on? It depends on temperature. Let me give you an example. If the delta S is a small value, which in many cases it is, then T delta S is also a small value. But if the temperature is very big, if temperature is very high, then T delta S can become a big value, can become a very large value, and it will later overpower the overall answer just because temperature was huge. Let's consider another example. Let's put it entirely over here. Let's consider another example. In another example, I'm considering an endothermic reaction with positive entropy. You have always studied that endothermic reactions don't go to completion as much, but positive entropy reactions want to go completion. So how do we understand such a case? Let's come back to the equation delta G is equals to delta H minus T delta S. if the entropy change is positive, T is because of the equation, minus because of the equation, and endothermic reaction means that positive enthalpy is here. If delta S is equals to positive like I just said, then T delta S is also a positive value, and minus T delta S is equals to a negative value. My final equation becomes positive enthalpy with a negative T delta S term, which is entirely over here. Now, what could be the final result? It again trickles down to the temperature value. If temperature value is small, then this negative value would also be small. But if the temperature value is really big, then the negative term would also be very big, and then it can overpower the answer. So the temperature has a major role over here. How do we calculate the temperature at which the reactions suddenly becomes feasible? So we know that delta G is equals to delta H minus T delta S. For the reaction to be feasible, delta G has to be negative, which means less than 0. It's a feasibility. For feasibility, the delta G should be less than 0. So you can either consider it 0 with an equality, or you can consider it less than 0 like this. Delta H minus T delta S. And then you can solve it like this. Let me show you. You can do it T delta S is more than delta H, and then you solve it like T is more than delta H divided by delta S. You can solve this fraction to find that this should be less than the temperature should be more than this fraction, and in that case you will find the temperature. So you can just take the ratio of delta H over delta S, and this ratio should be smaller than the temperature. So you can just predict the temperature by using this calculation. In today's video, we talked about the concept of Gibbs free energy. We talked about how the derivation is done. We talked about negative Gibbs free energy supports feasibility. We talked about two cases where exothermic reactions with negative entropy and endothermic reactions with positive entropy can have Gibbs free energy of negative only when the terms support this condition. Then we found how to calculate the temperature where suddenly feasibility begins, and the next video will be doing some past papers. Stay tuned guys. Thanks.